Okay, I gave you this basic notions of RLS, because I think I spent quite some time in explaining, I mean, what is our approach in RLS. Okay, I mean, what is the advantage vis-a-vis LMS and all those things we discussed, right? So that I am not going into. Yesterday I introduced one factor called forgetting factor, by which contribution in an inner product from the distant past can be ignored or can be suppressed, and mostly contributions from the recent samples will be taken into account. Okay. So, in that context, I have to say something. Suppose you consider some sequence, okay, some sequence, say Pn, P0, P1 dot 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 up to say Pn, and it is a random process, ergodic and all that. Then at each Pn, Pk, any Pk for any k is say some constant mu p, stationary, unless stationary it cannot be ergodic. Okay, suppose this is given, and in that case one way to estimate this mu p is only in that case I told you that if you assume the process to be ergodic, then ensemble average and time average they turn out to be same. So, in that if I assume to be this process to be ergodic, not only stationary, ergodic, then one way to find out mu p is to take averages, I mean to go on adding and then dividing. Okay, that is, suppose mu p cap will be what, 1 by n okay. It will be better, I mean we normally say that it will be better if you take more samples than average, but mathematically actually what it means, that is what I want to know. I mean we all know that if you take, instead of 100 samples, if you take say 1000 samples and average, you will get a better estimate. But actually mathematically what happens? I mean that is a qualitative statement, isn't it? First, if you just take this quantity, suppose you are observing this every time, you are finding out this sum, then this is also random. Look at it mathematically. If I carry out a sum like this without caring for any other thing, if I just carry out a sum like this is a stationary process, this quantity, this observation every time will be random, but the mean of that will be mean of this, each E p n is mu p times n, or maybe it should be n plus 1, sorry, because there are n plus 1 samples, 0 to n plus 1. So, mu p into n plus 1 divided by n plus 1. So, this is exactly mu p. Okay. So, if you take this sum, I mean take the samples, say n plus 1 number of samples, average, you get a quantity which is random. We make a qualitative statement that if you take more and more samples, if n is very large, this is a good estimate of mu p, but that is what we have been told in some context earlier, that you should take lot of samples for getting good statistical average, but mathematically what does it imply actually? That is what I am trying to come at. Here, whatever be the number of samples, if you take this quantity is random quantity, its mean is mu p, about that there is no doubt. Question is then variance of this error in this is its mean is mu p, but every time you measure it, you run this summation, you get something. So, the mu p cap and mu p they are not same, there is always some error. That error variance, I am telling you, you take it as an exercise, you replace mu p cap by this formula and mu p we know, square it up, okay, you will see this entire quantity is inversely proportional to n. I am not deriving it, and that is why this variance will go down. It might be inversely proportional to n or n square, this I do not remember, but I mean inversely proportional to either n or n square, this you need to check. This is a very simple exercise, mu p cap you replace by this and take this error to square it up. It will be simple, and then apply E and all that. You will see the entire thing has got I think 1 by n. I mean, it is inversely proportional to n. That is why if you take larger and larger samples, this error variance will come down. That is what is meant physically. When you make that statement that you should take more and more samples, it basically mean your estimation error variance will go down to 0 as n tends to infinity. Okay. Now, suppose instead of doing this kind of averaging, I am introducing a factor lambda, real, lambda real, and I am doing an average. I am doing things like this: lambda to the power k p k, lambda to the power n minus k p k. So, you understand at k equal to 0, I have a lambda to the power n, isn't it? Lambda is less than 1. So, naturally that is maximally suppressed at k equal to 0, then k equal to 1, then and at the current index k equal to n is lambda to the power 0. Suppose I find out this quantity. This quantity is also random. Every time you measure this, you are given a sequence, you are just running a sum. Instead of an ordinary sum like this, you are finding a weighted sum. This is also random. So, if you take the mean of this quantity, what it will be? Can you tell me? E of this will be what? E of pk is mu p into a GP series, isn't it? 1 lambda square dot up to lambda to the power n. So, that means mu p times 1 minus isn't it? So, therefore, if I have a factor here 1 minus lambda by 1 minus lambda to the power n plus 1, if I evaluate this quantity, its mean will be mu p. Its mean will be mu p. And then you find out this quantity, you call this mu p prime, again mu p prime and mu p square and all that thing. Again here you will see that it may not be so simple as here, but again that variance will go down as n tends to infinity. Okay. So, that means we can use this kind of averaging also. Then if you do further analysis, you will see that here you to get into the same tolerance band, you need more samples here than this. That is a separate matter, because you are suppressing some samples which you are not doing that. Okay. Those further analysis can be done, though it is of no consequence here. You have to just hear me out here. Okay. But in the extreme case of very large n or n tending to infinity, again here also variance will go down to 0. This you can verify also. It will be a clumsy kind of mathematics. After all, you have to replace this mu p prime by this here and then, but someone can try. Okay. So, mean will always be mu p and variance will go down to 0. May not be as fast as here, but it will go down to 0, and it is not very slow also. Okay. Now, consider that vector space treatment. I modify the inner product between two vectors where x say x q did I put subscript there yesterday? No? X, yeah, subscript, okay. All are real, no conjugate. This is Q. I equal to 1, just because instead of 0 I start at 1, I equal to 1, at I equal to 1 I should have lambda to the power q. Just a minute. Say I start at x 0. Q minus k So, if they are taken from a time series from a random sequence, this will be every time you evaluate the inner product, it is a random quantity, but its mean will be the actual correlation. You understand, it will be correlation between x I and any x sample and any y sample, because I am assuming jointly stationary and ergodic and all that. This also satisfies all the basic notions of those axioms of inner product, linearity in x, then if you see x, C will come out, that immediately you can see. And x with x will be what? This times mod x, y mod, this everything is real, so x square, this is already positive. If you have a quantity like x q square plus lambda x q minus 1 square plus dot dot plus lambda to the power q x 0 square, if suppose this is 0, norm square is 0, this current lambda is given to be positive. So, obviously, every term has to be 0 and therefore, lambda being not 0, each of the samples will be 0. So, that axiom 4 also is satisfied. Okay. We will be using this. This where that earlier I was taking this thing dn, just for remembering, it was from d0, d1 dot 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 dn. This I was projecting on what? Span of, there is w, I think I gave the span of x1n dot dot xqn. Remember, where any xin was xi0 dot dot xin. I was projecting on this, then projecting means I find a linear combination of this, I formed a matrix xn with these as columns. I have to find a linear combiner coefficient, so that this matrix times that coefficient vector minus subtracted from this, that is the error, norm square of that error earlier with that previous inner product definition when lambda was not present. What did we do there? We took this vector, formed a linear combination of this by a set of coefficients C1n multiplying x1n, C2n multiplying x2n dot 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 CQn xn, summation of that subtracted from this, that is the error. I took the error norm square, means first entry of the error vector square up, second entry of the error square up, third entry of the error vector square up, like that, and add. It was simple sum of square. That is what we are minimizing, which was equivalent to orthogonal projection of dn on that. That was minimizing that norm. But that time I told you that if at any index n naught, as you go from 0 to n naught, if the statistics changes, then until and unless you forget the previous contributions, because statistics changes means R inverse P, the optimal filter expression changes. So, optimum linear combiner thing changes. So, if you can forget terms before n naught and take lot of data after n naught, then obviously you will get the new set of optimal coefficients. But during the transition phase, the problem is you are taking more data from the past, combining only a few from the new n naught plus 1, maybe n naught plus 2. So, you get a set of optimal combiner coefficients which are in between, which are neither the new one nor the old one. So, that phase is the phase of uncertainty, that phase I have to minimize. As I go a slide forward from n naught to n naught plus 1 to n naught plus 2 to n naught plus dot dot dot, very soon contribution from the past before n naught should start disappearing, and only data from time index at n naught, time index equal to n naught or afterwards should be dominant. Okay. That is why I introduced that lambda factor. If you now use this inner product, here I minimize the norm square of the error with respect to this inner product, then obviously if there is any n naught index here, after n naught, after a very little while, you will be forgetting the contribution here. Okay. You will be taking contribution from the data starting at n naught and afterwards. Okay. So, that business will be gone. But one thing is there, at any point, suppose n naught has not taken place, suppose we are now considering a situation where statistics is not changing and all. So, earlier I give you this thing epsilon n square. Okay. I said that epsilon n square I am minimizing Why I am measuring epsilon n square? Because epsilon n square was actually approaching epsilon square for large n. That is what I said. What is the basis of that? That is what I discussed in the beginning today. What was epsilon square earlier? It was sum of the squares. Sum of the squares divided by, say, an average, that averaging factor, number of terms. That for large number of such terms would approach epsilon square. I told you in the beginning today, when you are doing averaging, in the sum of square, previously lambda was 1, isn't it? If you are finding the error vector E n as d n minus x n c n. C n we know is C 1 n, C 1 or what? C 1 n dot dot C q n. This error vector earlier, what we did with lambda 1, that is the previous inner product. What we did? We took to the norm square. Norm square means every element of this error vector squared added. That will be that was we are minimizing with respect to this. So, that sum of square you can even divide it by the number of terms. That will not change the optimal thing, because number of terms and C they are independent, they are not related. Okay. But when you take the sum of square and divide by that number of terms n plus 1, then according to previous discussion today, that will be a good estimate of this, provided n is large. Mean of that will always be actual epsilon square, but variance will go down. So, whatever you get, that will approach this, that we discussed in the morning. Question is, what happens with respect to the new inner product? In the new inner product, it is not simply sum of squares of the error, weighted sum of squares. Okay. It will be like lambda to the power n is square 0. Okay. Lambda to the power n minus 1 is square 1 dot 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 lambda e n minus 1 plus e n. This we want to minimize with respect to this coefficients, because E n vector from that E 0, E 1 up to E n comes, and those terms depend on the optimal coefficients. So, this is a quadratic function of the filter coefficient, this you minimize. Okay. In fact, you can also introduce that factor 1 minus lambda by 1 minus lambda to the power n plus 1 here times this, because whether you minimize the entire thing or minimize this, you will get the same coefficients C n, isn't it? Because this has no C n here. You will be differentiating this with respect to each filter coefficient, combiner coefficient. So, whether you have this factor here or not, it does not matter. Okay. Suppose I bring this factor. In that case, this one, like earlier I did not bring the factor, lambda was 1 and I simply put a n plus 1 factor below, and I said this is a good average. If n is large, according to previous discussion, that would approach epsilon square fair enough. I have made it slightly different. So, I have to recheck things here. Now, sum of square has become a weighted sum of squares like this, and instead of n plus 1 in the denominator, I bring this quantity. Still, if I minimize this with respect to the filter coefficients, I will get the same ones, because this factor does not change my optimization. Dependence on the filter coefficients is in this E 0, E 1, E n, not here. But as I go for minimizing, I am minimizing the entire quantity with respect to the coefficients. But what is this quantity? This is saw in the beginning today, that mean of this quantity is again this epsilon square. Mean of this quantity is again epsilon square, and this also for large n, I told you variance of this quantity also will go to 0. Variance of this minus, if you call it epsilon n square minus actual epsilon square, that variance, I mean difference, if it is the variance of that, that will also approach 0 as n tends to infinity, according to the discussion in the morning today. Okay. So, that means jolly well I can as well optimize this, and the coefficients I get, they will also approach the optimal filter ones, because this is also approaching epsilon square. Epsilon square when minimized with respect to the combiner coefficients gives you that R inverse P, the optimal ones. Okay. So, earlier I took simple epsilon n square, no weighted sum, now I am taking this, but even here also I should get back the same optimal filter coefficients, because after all this also will tend to epsilon square for large n. Okay. So, instead of that simple this thing, I mean sum of squares, so we will be taking this weighted sum of squares now. That is why I will be using this inner product, fine. because I will get in any case the same optimal filter coefficient. That is what I wanted to say so far. So, that means this quantity this quantity you can see, you can write as X transpose a matrix delta Q y, where delta Q is a diagonal matrix this. Here focus on this and these three, x k y k, and I am saying x transpose, this is x vector, y vector, Can you see it easily? This is, isn't it? So, this is what, and this matrix depends on Q because of this factor Q. Okay. If you have that x row vector and y column vector, multiply, you will get this, you can easily see x 0 into y 0 into lambda q, x 1 into y 1 into lambda to the power q minus 1 dot 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 and all added. Fine. So, this is how I will be writing. So, that means now what will be my optimal coefficients as I minimize with respect to minimize this sum of square, weighted sum of squares with respect to the new inner product. How to find that? I will follow the same procedure, that is I will take the error, I am doing the orthogonal with respect to this inner product only, I am carrying out orthogonal projection, that means projection error is orthogonal to this space W n. So, I will find the error, inner product I will compute of that, I mean with that error, I mean between the error and each of these function and each of these vectors, and that will be 0. I will have to use the same thing, that is E n was, I am rewriting, this is much of whatever I discussed so far is a repetition actually. So, E n, I have to take the inner product between whom E n vector and each column here. What is the meaning, how to carry out the inner product? As per the new definition, I have to have one delta n, it is called what? Sorry, lambda n, sorry, thank you very much, lambda n, I mean delta is, big delta is really delta, this is a bridge here, lambda n and any vector from here, that will put a row form, x transpose this y, isn't it? Earlier this was not present, it was simply row column. So, that means first column here is x 1 n. So, that will be x 1 n transpose, that will be 0. Next column is x 2 n transpose with this 0 because of orthogonality, inner product between E n and each of the columns is 0. So, as well I can put like this, after x n matrix, first column x 1 n, after transposition that becomes first row, x 1 n column vector becomes x 1 transpose n. First column gives rise to first row, second column gives rise to second row, isn't it, after transposition. So, first this will become your 0, a 0 vector of length q because there are q terms here, q column vectors. Say absolutely same treatment, but E n is this, E n is this. So, you replace E n by this expression. This gives rise to what? C cap n you can even put as what? More generalized form than earlier. Okay. And once again invertibility of this, you understand, what I am doing is, earlier I did not have this lambda n, I got up to this, I gave all the explanation and everything. Now, today with this in the new context also, I have to carry out the same treatment. What is the guarantee that this matrix will be invertible? For that, you see one thing, earlier I said x transpose into x is positive, non-negative definite. That will be valid here also. How? See the trick, delta this lambda n I can write as lambda n to the power half is a more matrix. I will define what this matrix is. Again lambda n to the power, it is called square root matrix. Half is nothing but, since all lambdas are real, square lambda to the power, earlier it was n, now it is n by 2. Lambda to the power n minus 1 by 2, dot 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 lambda to the power 1 by 2, then 1. If you define this matrix, if you multiply these two, you will get original lambda. Agreed? And then lambda n half into x n, you call it x prime n. So, obviously, this is x prime n, sorry, and this is also symmetric, lambda is a these are symmetric matrices, diagonal matrix, symmetric matrices. So, you can write like this x prime n, x prime transpose n, first x prime n is this part here, and its transpose, so x transpose and transpose of this, but transpose is itself, that comes and these two multiply, you get lambda n. This is a positive semi-definite, non-negative definite matrix, also called positive definite. Okay. So, it has always eigenvalues real and non-negative, real and non-negative, but for it to be invertible, eigenvalues should be strictly non-zero. That means, it should be positive definite. This is what you did last time also. So, what is the requirement for that? That x prime n should be such a matrix that there should be no linear, the columns should be linearly independent. That is possible only if you are taking n, that is number of row is at least equal to number of columns or more, otherwise it is not possible. This is a repetition of all that we do. So, so that is valid here also. Okay. That is valid here also. That is number of rows. You understand, you remember na, this x prime n, what are the rows? N equal to 0, 1 row, n equal to 1, 1 row, dot dot dot, n equal to, I mean I have got how many columns? Q columns. So, n equal to q minus 1. These rows, how many rows? Q. So, n should be at least q minus 1 or higher. If n is less than q minus 1, obviously, I have got more columns than rows. So, some column will be, but that means, but dimension is n, dimension of the vector space is n, number of vectors, number of columns is more than n. So, at least one column should be expressible as a linear combination of the other. Okay. Even if I have got n number of linearly independent vectors, there are more than n, because q is greater than n. So, q minus n extra vectors, each of them should be expressible as a linear combination of the rest. So, immediately then you remember that positive definiteness goes, I can find out a linear some vector here a, which will give us to this into a equal to 0, where a is non-zero, and that will correspond to eigenvector of that way, eigenvalue 0. All this I did last time, right. So, again this is the condition, that first n should be at least q minus 1 or greater, and there should be no linear relation between the columns of x prime n otherwise. But this x prime n, I have to talk in terms of original x n, x prime n and original x n. I am saying that the coefficients of the columns of x prime n should be linearly independent. There should be no linear relation between them. In terms of x n, what does it mean? Columns of x prime n and columns of x n, how are they related? You scale the rows. Okay. That will not change your linear dependence thing. If suppose columns of x prime n are linearly independent, please do it yourself, then show that columns of x n also are linearly independent. Okay. You can do it very easily, this way. Suppose this is lambda into the power half into x n equal to this. This is a square matrix. So, that means x n is into x prime n. Okay. And then from x prime n you can infer about, you do it as an take it as an exercise. Then we do it this way. So, then in conclusion we can do all those things with respect to the new inner product. Now, I march to this topic of today, that is RLS adaptive lattice. I am assuming that my data sequence x n, which is a random sequence, is starting at n equal to 0. Okay, so, data before n equal to 0 will assume to be 0. This is called pre-windowed case. Pre-windowed, this is particular case of this lattice filter. There are other extensions where you are not assuming data to be 0 before n equal to 0, but suppose I am assuming here, because that is always the case, because you switch on somewhere at some point of time, isn't it? So, 0 initial conditions. Okay. So, you define the vector x n as x 0, x 1 dot 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 x n. So far so good. Then define this, they give me some z to the power say minus q for any integer q x n. It will be delayed, like the sequence, original sequence is delayed q times. That means, first q locations will be zeros, pre-windowed case, any data before n equal to 0 to the left of origin is 0. So, those zeros are coming in. So, how many zeros? Q zeros, and then x 0, x 1 dot 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 okay. W say k p n span of you will understand why I did that lattice, stochastic lattice in that projection framework using vector space. The treatment will be overlapping, I mean, this framework will be same in some places, most of our places I would say. Fine. I am assuming, of course, p greater than equal to k and greater than 1, greater than equal to 1. So, at least one term is there, z to the power minus 1, or maybe here you can set it to the minus 2, it is okay in this definition. This is W k p n. Okay. This is a span p k p n. Remember, in the stochastic lattice case, I did not introduce this, I did not have this n in the subscript, because I told you using stationarity, all whatever I do, n will disappear. So, you can jolly well, I mean, whatever you do get, result you get out of index n, if you replace n by m, you will get the same result because of stationarity. I was not using n here, here it is not. Everywhere I have to bring this, keep this n here. There is no e operator, no stationarity business, nothing. Please understand, there will be no e operator anywhere. There will be exact computational linear algebra. You know very well, ortho projection of for and orthogonal projection error operator for this. Okay. Then define E p. Earlier I had this vector E p f n. First define and then see what is meaning actually. E p f n as sorry, x p1 p x, that's okay, p1 1 p, yeah. Firstly, since first time using what is, first forget about this projection error, take just a projection. What does this projection mean? On one hand you have got x n vector, and what is the space here? Z to the span of z to the power minus 1 x n to z to the power minus p x n. So, last, take the last elements of each column vector. Here I have got x n and here I have got x, here how much? Z to the power minus 1 x n means 1 0. So, last element will be x n minus 1, next one will be x n minus 2, next one will be x n minus p, is not it? Previous, then before that will be x n minus 1, so x n minus 2, x n minus 3 dot 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 x n minus p minus 1 dot 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 dot, and here it will be x 0, here 0, because x minus 1 is 0, x minus 2 is 0, 0, 0, 0. This is the situation. Okay. Is this letter size coming to be small? Can you see this? Because I get a feedback that size is possibly small. Is it okay, this size, letter size? Okay. So, when I do projection means the projection of this vector on the space spanned by these columns. This is one column, this is one column, this is one column, this is one column, space spanned by these column vectors. That means what? I will be linearly combining them by a set of combiner coefficients and take the sum of square of the errors with that weight lambda. Lambda we forget for the time being. For the time being assume known lambda, lambda equal to 1 say. Then what is happening? You are finding out a combiner coefficient so that x n minus a linear combination of past p samples. Then x n minus 1 a linear combination of past p samples, dot dot dot, you are finding out the error, square up and summing. If you minimize this, because that normally will be, I mean, if you take the error, square up and take the sum, that is the norm square. If you minimize this, then only you are computing orthogonal projection, but if you minimize this with respect to the combiner coefficients, then for large n, those combiner coefficients indeed will be the optimal forward predictor coefficients, isn't it? And this projection will be indeed the optimal, the actual forward prediction. But with those coefficients, you will get a vector. With those coefficients, when I combine the columns, you will get a vector. Vector of what? Orthogonal projection. If n is larger and larger, if from n you go to n plus 1 or n plus 2, you will get a new set of coefficients. By that you combine these columns, you will still get a vector, maybe of length n plus 1 or then n plus 2, but this initial part will be common. But initial part common means this projections will be better projections then. This I discussed. This I discussed at length for half an hour in the very last class. I am just trying to show what does it mean here. That this will give indeed give rise to, I mean P1P and Xn will indeed give rise to, I mean if you take this vector, projection vector, the last coefficient, latest coefficient, current term, latest term, current term, that will indeed turn out to be the actual prediction error, pth order forward prediction error, when you have taken a lot of data, isn't it? Huh? Because I am, what I am doing, I am instead of, I no longer have that correlation things on E operator. So, I am instead of having this exact value of the prediction error variance, which we are minimizing that time, prediction error variance was the norm square of the error there, prediction error there. What I am doing, I am finding out linear combiner, subtract from x n, get one sample error, another sample error, and I am squaring up the error, adding, minimizing it. That is computing orthogonal projection. But minimizing that error means what? For large n, that error will be approaching the actual epsilon square, that is actual prediction error variance.
But sir, in this case, x0, x1, are they not contributing more error because
No.
they are mapped in zeros also? X0, x1 is contributing more error
How?
because
No, we just system is such that indeed you have got 0 before x 0, then I am not introducing any error. This data is not erroneous. Na? Your question is,
we are projecting x0 on those zeros.
I am not projecting a particular sample on those zeros. I have got a random sequence. I am taking any sample at nth index and finding out a linear combination of past p values, taking the error, square of the error, again do the same thing at n minus 1th index, n minus 2th index, like that, adding up the errors, so that I get a good estimate of the actual error variance, stochastically obtained variance, that I am minimizing. So, if I take large number of samples, the sum of square thing will indeed tend to be a good estimate of, in fact, we will converge on the actual variance E operated on the prediction error variance square. Okay. And therefore, the combiner coefficients will also give you the optimal ones. Okay. And therefore, the projection will be, if you take the, and with those optimal ones you combine these vectors, you will get a vector, but I am only interested in the current component, latest component, because that is the index where I am standing, there is a current time index. You will get previous components also, which will be a better estimate of the projection, because you are using, you use more data than earlier, and therefore, you got a better combiner coefficients. But I am not bothered about x, I mean the index 0 or index 1 or index 2 anymore, isn't it? I am only bothered about the current index. If you take out that component, that is, if you take the, this is a vector, if you take the nth component of this vector, that is what I will be focusing on. And that, if total number of samples taken is very large, then that component will indeed be, I mean, the actual forward prediction error obtained in the lattice earlier. Okay. That is what will be understood or not? Is this approach clear? So, this is my definition. By the same token, I now define sorry, this is p minus 1. You can see this z to the power minus p x n means this guy. This guy will be projected on what? The space spanned by the previous fellows along with x n. This will be x n, z to the power minus x n, z to the power minus 2 x n up to the one before this, space spanned by that, on that I will project this. That will give rise to backward projection. After all, what is the last entry here? X n minus p. That are now, that you are not linearly combining as in terms of these fellows, isn't it? P future terms standing at n minus p. Taking that error again here, squaring up all those errors, sum, minimizing. That is how you are computing this projection. But sum of that square error will be what? A good estimate of the actual backward prediction error, pth order backward prediction error, isn't it? If total number of samples is very large. So, you minimize that as you compute the orthogonal projection, those coefficient, combiner coefficients indeed will converge on this optimal backward prediction error coefficients. Same logic for what I had for forward prediction, same for backward prediction. And therefore, with those optimal, with those linear combiner coefficients, if I combine them, I get a vector. I am interested only in the latest component, and that component will be what? Some combination of these fellows, which will be a very good estimate of the actual pth order backward prediction error at index n. Okay. This is my definition, and now I have to, from this I have to find out. And one thing I should tell, let us consider this, from this I have to find out E p plus 1 f n, E p plus 1 b n. Approach will be very similar to what we did there in that stochastic lattice. Okay. But just before that, there are places where things are different, and we should be very cautious. Look at this space here, say in the forward prediction error p 1 to p n, or here say p 0 to p minus 1 n. Just take one of the two, say here. Here what I have got? How many terms? How many terms? P terms. How many columns here? P columns. You have to assume, mind you, this column will start at x 0 and go downward. This will start at 0 and then x 0 data, 0 and then data, 0 0 data, 0 0 0 data. All the analysis for the time being, you assume that we are doing for index n greater than equal to the total number of rows. How many rows are, total number of columns? How many columns are there? P. N starting at 0. So, n is greater than equal to p minus 1. That is true here also, that is true here also, because you can see easily number of column in either case is p. Okay. Assume that we are doing all this analysis for n higher than the number of columns present in the respective data matrices. Okay. Otherwise, that problem of that thing will come up. Okay. Dependence and independence will come up. This we assume, and how that time it was showing up when you computed that exact that matrix. Okay. When you computed the C cap n directly by this, but we will not be doing like this, na? Will be, because that is a direct computation. We will be obtaining them recursively. When you obtain it directly, at that time it was showing up clearly that this should be invertible and all that. But in the recursive procedure, no such matrix based computation will be done, no such inversion will come up directly. But this phenomenon will reveal in a different way, that okay, that columns of x n must be linearly independent. Otherwise, unique solution does not, this is not, this solution does not exist. In the recursive phenomenon also, algorithm which will this will come up in a different way. In a direct computation, it comes this way, that okay, inverse does not exist, but we will not be using direct computation, we will be using a recursive, we will develop a recursive algorithm, but that phenomenon is crucial there also. That we will see that how the linear independence of columns will be required, and there is how number of rows should be greater than or equal to number of columns. Okay. That will reveal here in an indirect way, not the way it is comes here, that okay, inverse of a matrix comes up and the inverse does not exist and all that. Okay. So, now WKPN So, suppose I want to WK p plus 1 n, very quickly that will be WK, this treatment is absolutely similar to what we had there, WK p plus 1 n, not WK, W1 p plus 1 n. Here I had W1 p n, W1 p plus 1 n will be W1 p n and direct sum what? This guy. Okay, this needs to be explained. We are, let us go slowly, because things, even though there is similarity between lattice and this, at every step, there is some new element. So, let us not run through it. What we are doing, we are giving EPFN and EPBN, we want to find out the same quantity, same vectors for p plus 1th order, p plus 1th order and the same index n, and then I will take the last component. Taking the last component is not a problem. The same thing I have to do. Now, so that means the space will be for finding out EPFN, EP plus 1 Fn, what will be the space? Earlier it was W1P, now it will be W1P plus 1, about that there is no doubt. What is this space? The span of, there is a very nice thing here. Sorry, z to the power minus 2, z to the power minus 1, because 1, first p, then I will write that separately. Okay. This part I take out separately, the span of that will give rise to W1 p n. About that there is no doubt, 1 p n, about that there is no doubt. Okay. Question is, this will be direct sum of, there will be direct sum of, this entire thing will be this space direct sum with the span of what? If you take this guy project it orthogonally on this space, take the error, span of that. There is a slight difference between EPBN and that thing. Okay, there is a slight difference. It's not coming directly. It's not so nice as in the case of stochastic lattice where stationarity was used and n was dropped. Here, biggest problem comes because of the presence of n. That time, n was the index n was missing and lot of I could play around, but here n is present everywhere. This guy, please see the inner dynamics. I don't know whether I have so much time or not. This guy is to be projected on this space. First fellow top entry of each of the columns is 0, start at z to the power minus 1. When I do the orthogonal projection, what I will be doing? I will be linearly combining them, and then last entry I subtract from the last entry here. Last but one entry of that combined thing subtracted from here. I will take that errors, square of the errors. Topmost entry will be what? Combined value of zeros minus subtracted from 0, it will be 0, and sum of square of the error. I will be weighting them. Weighting them how? That is, if you consider this part to be this matrix, you take x, you put the columns in a matrix from 1 p n. 1 because z to the power minus 1 x n goes up to p and n. I am putting them as a column of a matrix. This matrix is to be multiplied by a set of combiner coefficients. How many? 1 to p. So, it is a length p vector. That is the projection. This minus, I am projecting this orthogonally on this. Okay. So, this is what I have to do. Minus this is that error, isn't it? I do not know what error is, I have not given any name to it. So, you say call it theta n, no problem. But what is theta 0? I will be taking this theta n and I will be, what is theta 0 by the way? 0, because top guy first row of this matrix is all 0, because z inverse 1, z inverse 2, z inverse p, first row here, first element here also 0. So, theta 0, and now I will be what? I will be doing what? I will be minimizing lambda to the power n theta 0 square plus lambda to the power theta 1 square dot lambda theta n minus 1 plus theta n, sorry, theta square. This quantity I will be minimizing, isn't it? But this guy is 0, forget this is equal to 0. And what is this quantity? Suppose I am now standing at index n minus 1, suppose I am standing at index n minus 1 here, and I want to find out the backward prediction error vector pth order, but at index n minus 1. That is, current index is not n, but n minus 1. Then this vector would be what? Z to the power minus p x n minus 1, isn't it? What would it go to? I think there is no time today. I mean, this is just we will come with this thing. So, I will continue from here in the next class. You please come prepared with just this background, because this will take at least 10 minutes, to explain. So, when do we meet next? Okay. Fine. Thank you.